Hey guys, welcome back to another lecture video for Chem 104. In this lecture video, we're going to cover several topics involving alkenes and alkynes. The first topic that we're going to discuss is simply understanding what alkenes and alkynes are and their physical properties. Then we're going to go ahead and talk about how we can represent alkenes and alkynes in several structures. So for example, the condensed structure, the expanded structure, and the skeletal structure. And then the last thing that we're going to cover in this lecture video is naming alkenes. And so we are going to name alkynes in another lecture video. All right, so let's get started. So what are alkenes and alkynes? And so alkenes and alkynes, they belong to the hydrocarbon family, right? So imagine an organic compound filled with just carbons and hydrogens. However, if you guys have a double bond in your organic compound, then you would use the suffix ene to communicate to the reader that there is a double bond somewhere in the parent chain. A parent chain in an organic compound can either have 1, 2, or 3, or even many double bonds, depending on the length of the chain. And so some fatty acids, some lipids have numerous double bonds, and hopefully we'll be able to see that within this semester. So alkynes, on the other hand, they are organic compounds that contain a triple bond somewhere in the parent chain. And so the suffix yne, it's pronounced as "-ine", it's going to communicate to the reader, or you're communicating to another scientist, that there is a triple bond present somewhere in the organic compound. Okay. And so let's go ahead and talk about the physical properties of alkenes and alkynes before we start looking at how to draw them and how to name them. And so alkenes are unsaturated hydrocarbons. So this word unsaturated, we've seen it once before when we were talking about cycloalkanes. And so in short, anything that's unsaturated does not contain the maximum number of hydrogen atoms that carbon could have, right? And so if you guys recall, a carbon needs to have 4 covalent bonds. And so if all 4 of the bonds that's surrounding carbon is hydrogen, then you would say that this is a saturated carbon. If, for instance, this carbon is covalently bonded to another carbon, such that both carbons have 3 hydrogens surrounding it, then we would say that this molecule is saturated as well. And so when you guys are talking about an alkene, an unsaturated hydrocarbon, you're removing these hydrogens. So these hydrogens are going away to form that double bond. And if you guys look, I still have 1, 2, 3, 4 covalent bonds on this carbon on the left. And I have 1, 2, 3, 4 covalent bonds for this carbon on the right. So I'm still following my octet rule. And just removing those 2 hydrogens and creating a double bond produces an unsaturated hydrocarbon. All right. And so its overall general formula can be described mathematically as CnH2n. So this is the chemical formula for an alkene. And we've seen this before. If you guys go back to a few lecture videos, this is also the same formula for cycloalkanes. Okay. And so one can say it's, just by coincidence that they both have the same chemical formula. But if you guys are thinking about creating a cycloalkanes, you'll also see that 2 hydrogens were removed to form that covalent bond. So for example, if you have CH2, well, let me see here. So let's just say that we're trying to make cyclo. And at this point in time, this carbon is still considered saturated because it has a maximum number of hydrogens that is possible given that it is covalently bonded to 2 other carbons. Okay. Now, for you to create a cyclic alkane, you're going to go ahead and remove 2 of these hydrogens and replace that with a single bond. And if you guys count the number of covalent bonds, we still have 1, 2, 3, 4. So that fulfills carbon's octet. And here we have 1, 2, 3, 4. And that also fulfills carbon's octet. Let me move this up so you guys can see that carbon that's just kind of hidden. Okay. And so since 2 hydrogens were removed to form either a double bond or a ring, it would make sense that both alkenes and cycloalkanes have the same general formula. All right, so let's go ahead and take a look at this structure. So the simplest alkene in organic chemistry is a 2-carbon compound. So the minimum number for you to have a double bond is 2 carbons. And so ethylene is a common hydrocarbon that's typically colorless, and it's a flammable gas. And if it's pure, if you guys have pure a vial of pure ethylene, and if you kind of waft, when you kind of waft it to your nose, it will have like this sweet and musky odor to it. And so ethylene, interestingly enough, has a lot of biological effects. For example, in plants, it stimulates root initiation, so the production of roots, and it also controls the formation of root nodules in legumes, so like beans. And it also inhibits the formation of storage organs as tubers, such as tubers and bulbs, and it promotes flowering in some species, but yet for others it inhibits it. And so, long story short, ethylene plays a huge role in terms of biological functions or biochemical functions for plants. In the food industry, ethylene is used to artificially ripen some fruits. So for example, like bananas are typically picked when they're green. And then they're going to producers, once it's shipped to its actual location, it's going to be gassed with ethylene to artificially ripen the banana. And so it's crazy that we have this simple 2-carbon compound, yet it has so many effects in both plants and in the food industry, amongst many other functions that it has. Now, if you guys are talking about the 3-dimensional character for these double bonded carbons, if you kind of imagine having 2 toothpicks and lay them side by side, just like this, And then you guys are going to stick like 2 marshmallows on either end of those toothpicks. And if you were to pick that up and kind of like rotate it around you, so if you guys can imagine picking this structure up, bringing it up to eye level, and if you guys rotate it towards the side, it's going to be flat. Okay? And the reason why is because its electron configuration, its electron geometry is trigonal planar. And so remember that trigonal planar has 120 degrees between, so that's the bond angle, it's 120 degrees on all sides. Well, it doesn't really have a side. So it's 120 degrees per angle, total giving you 360, so that's a circle. Now, if you were to pick up this ethylene and just kind of look at it on its side, you'll see that nothing is protruding to the left or right. It's just a flat molecule. Okay. All right. So for alkynes, once again, it's an unsaturated hydrocarbon. And if you guys are looking at an alkane, so we'll do ethane as our example. This is the expanded structure. For an alkyne or a triple bond to be formed, I need to get rid of 2 hydrogens. And that bond is going to go between the 2 carbons. And so to create a triple bond, so right now I have an alkene. To create a triple bond, I have to get rid of another 2 hydrogens. And then that bond is going to be between those 2 carbons. And once again, if you guys look at the number of covalent bonds that surrounds either carbon, it should reflect the octet rule. So here we have 1, 2, 3, 4, 5, 6, 7, 8 electrons for the carbon that's on the left. And if I change color to, for example, blue, here I have 1, 2 electrons, 3, 4, 5, 6, 7, 8 electrons for the carbon that's on the right. And so by removing those hydrogens and then taking those electrons and creating another bond between the 2 carbons, it produces a triple bond, but since we've reduced the maximum number of hydrogens possible, we would say that this is a unsaturated hydrocarbon. Okay. All right. And so alkynes, the general formula, it's not going to be similar to the cycloalkanes or alkenes. It's going to have its own formula, so to speak. So it's CnH2n minus 2. And so if you guys recall how to use this, let's just say that N, which is the number of carbons, is equal to 4, right? So if you have a 4-carbon compound, what would its chemical formula be? Well, you're just going to go ahead and plug in 4 into here, and you're going to plug 4 into here. And so here you would get C4H2 times 4 minus 2. So 4 times 2 is 8 minus 2 is 6. And so the chemical formula for an alkyne that has 4 carbons is going to be C4H6. Okay. And you guys can go ahead and do the same type of exercise for alkenes and cycloalkanes using this general formula, CnH2n. Okay. And so the simplest alkyne in organic chemistry is a 2-carbon compound. So that is the minimum requirement. You guys cannot have an alkene or an alkyne if you only have 1 carbon. You need to have 2 carbons. And so acetylene, and so remember that we're talking about ynes, right? YNE. So the reason why this one has an ENE in its name is because this is the common name that was given to this chemical compound before the IUPAC nomenclature existed. And so it was termed in 1864 by a French scientist. I can't really pronounce their name. It's Berthelot. Anyways, so basically it was termed in 1864 and it was kept that way. And the IUPAC nomenclature was created way after 1864. So sometimes the common name just kind of stuck. And so the true name of this 2-carbon compound is ethyne. Okay, remember I'm sorry, I shouldn't say true name. It's IUPAC name. That means if you apply all the rules that we've been discussing in the past several lecture videos, we would name this 2-carbon triple bond, 2-carbon structure with a triple bond between them as ethyne. Okay? But the common name is acetylene. And so acetylene has a lot of uses. Its primary use, it's not so much biological rather than industrial. And so it's typically used for welding and cutting. And so the welding process that uses acetylene is known as oxy-fuel cutting or gas cutting. And so you're burning this specific gas, this acetylene gas, to cut or meld materials that require temperatures as high as 3,500 degrees Celsius. And so in Fahrenheit, that's 6,330 degrees Fahrenheit. So that's pretty hot. And so acetylene is definitely capable of producing very hot flames. So it goes to show you that this simple 2-carbon compound can really produce a lot of energy, and it's probably coming from the burning of that triple bond. That's for a different lecture. All right, so let's go ahead and take a look at the 3-dimensional character of a triple bond. And so if you guys have 2 carbons and in between them there's a triple bond, then its electron geometry is going to be linear. And since it's linear, we have a bond angle of 180 degrees. So this is telling you that the ethyne or alkynes, just in general, are flat, very similar to alkenes. They don't have this 3-dimensional character that we observe for a tetrahedral. So if you guys recall, tetrahedral has one bond that's kind of protruding outwards, like above the plane, and another bond that's going behind the plane. So it's 3-dimensional in character. However, it looks like from what we've discussed, alkenes and alkynes are both flat. Okay. All right. And so in terms of its polarity, alkenes and alkynes, just like alkanes, they share very similar physical properties. So they all have non-polar covalent bonds. We have carbon to carbon, right? So since they have the same atom, then therefore their electronegativity difference is also the same. And the difference in electronegativity is 0, right? Their electronegativity values are the same since it's the same element. And so if you subtract those two numbers, like what we did in general chemistry, their difference in electronegativity is 0. So therefore, it is a non-polar covalent bond. And since we're dealing with solely carbons and hydrogens, as you guys can see from this picture, the intermolecular forces that's observed is pretty much non-polar. So non-polar to non-polar, so that's going to be van der Waals interaction. And so if you have like two ethanes or two ethenes, that's going to come close together. And if they kind of like bump each other and if they somehow attract, that attraction between those two gas particles is going to be most likely a van der Waals interaction. Okay. And so alkenes and alkynes, very similar to alkanes, they have low melting and boiling points, and they're also insoluble in water. Okay. And so since they're insoluble in water, we're going to form a heterogeneous solution. So let's just say that we have 3 test tubes. We fill each test tube with water, and then we add like a few drops of an alkyne in one test tube, an alkene in another test tube, an alkane in another test tube. And after we mix it, we should observe that all 3 of them will form a heterogeneous solution. In other words, we'll see 2 layers in which the top layer is going to represent the hydrocarbon. And how do I know the top layer will be a hydrocarbon? Well, let's look at their densities. And so remember, the density of water is 1. And so since the density of all of these alkanes, alkenes, and alkynes is less than 1, then they're just going to float. They're going to stay on top of water. And that really does help us in terms of like physical separation. So if you guys needed to physically separate like an alkene, alkyne, or alkane from water, they're having their densities to be different will create a heterogeneous solution. That way you can either boil it off or physically pipette it out. And so since alkenes and alkanes and alkynes, they have very low melting points and boiling points, we're just going to go ahead and observe. We're going to look at boiling point real quick. And so boiling point is the temperature in which the gas phase and the liquid phase are at an equilibrium. So anything above the boiling point, it's going to be gaseous in phase. Anything below the boiling point, it's going to be liquid in phase. And so this is just like the temperature, that delineation in which you'll have a transition between the 2 phases. And so if you guys look at ethane, ethene, ethyne, so this is a single bond, double bond, triple bond. You'll notice that there's really not like a strong correlation between the 2. Like if you go from single, double, triple, notice that it kind of fluctuates in boiling point. We have negative 88.6, negative 105, and then negative 83. However, if we start comparing those values to a 3-carbon chain, we'll start seeing like a pattern almost. And so notice how your triple bond is always the highest amongst the set, and then the alkane is going to be the second highest, and then your alkene, your double bond, is going to be the lowest. Okay. And so if you guys look at the ethenes, or the 2 carbons and the 3 carbons, just based on these values, you can kind of see a pattern emerge where your ethyne will typically, or your alkyne will typically have the higher boiling point, and then your alkene is going to be the lowest in boiling point. And then the alkane is just going to be like the middle ground between the 2. Okay. So you guys can go ahead and see it here as well. Let's see, yeah. So ene, that's double, 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 and then eine, triple, triple. Okay. So if you guys are looking at this set, you'll see that the triple bonds are going to have the highest boiling point. Okay. And so 1-butene, cis-2-butene, and trans-2-butene, it's the numbers are kind of fluctuating just because of the geometric orientation, and we'll talk about that when we discuss isomers. So this probably isn't a really good example to observe the conclusion that we made between these two sets. Okay. But, you know, in all scenarios, it looks like our triple bond is going to have the highest boiling point among all three of those hydrocarbons. Okay. Now, let's go ahead and talk about the condensed structure and the, well, first of all, let's talk about the expanded structure. So this is what the expanded structure of a double bond or a triple bond looks like. And we've seen it once before in a previous lecture video. And so notice that the number of carbons on a double bond, notice the number of hydrogens on the carbon that has the double bond is minimal, right? It's unsaturated. And it's even more unsaturated when you're looking at a triple bond. So notice that carbons on the triple bond, or the two carbons that shares a triple bond, they don't even have a lot of hydrogen. So like this one right here, oops, this carbon right here doesn't even have any hydrogens. And this guy right here, since it's a terminal carbon, it just happens to have one hydrogen. And so whenever you guys are writing the condensed structure of this, of a molecule that contains a double bond or a triple bond, you guys are just going to summarize the pieces just like what we did in the first lecture video for this lecture series. And so we're going to go ahead and summarize this section as CH3. We're going to summarize this section as CH2. Summarize this section as CH2. Summarize this section, or that carbon, as just CH. And then here we have another CH. And then here we just have C. And then here we have another CH. Now when we're writing this in terms of a condensed structure, we're going to go ahead and get rid of our single bond, but we're going to keep our double bonds and triple bonds. So here we have CH3, CH2, CH2, CH. Okay. And notice that this CH, which is this CH, is going to have a double bond. It's going to share that double bond with the other CH. So I need to make sure I communicate to the reader that's where the double bond is located. And then after that, I have a single bond. And then there's another carbon. So I'm just going to bring that carbon down. I'm going to ignore that single bond that's between them. And then the next item is a triple bond. So I'm going to put 1, 2, 3. And then last but not least, the carbon and the hydrogen. Okay. And so what I drew here is the condensed structure. Of this molecule. Okay. And so how can we depict this same structure in terms of skeletal? So to go from expanded structure to skeletal structure, we need to determine how many carbons we're working with. And remember, for the skeletal structure, we're ignoring the hydrogens. And so it really makes drawing this organic compound very simple. And so here we have 1, 2, 3, 4. And then on that fourth carbon that arbitrarily I've labeled as number 4, I have a double bond. So let's go ahead and do that. So I have 1. So the moment you put your pen or pencil down, that's 1, 2, 3, 4. So I'm here now. And so the next bond that I draw to get to 5 is going to be a double bond. So 1, 2. Okay, so this is now my 5th carbon. This is my 4th carbon. And then the next bond is a single bond to another carbon. And then the next bond is a triple bond. Now when you're drawing a triple bond, remember that it has to be 180 degrees. And so that means that you're going to draw a triple bond going up, do not bend it. And since the last is a carbon hydrogen, remember that we're ignoring the hydrogen, so we simply leave it as is. Okay? And so if I'm going to mark my carbons, I have 1, 2, 3, 4, 5, 6, 7. Okay? So don't forget that the end of a triple bond also contains a carbon. And if you guys look, I have 1, 2, 3, and you start erasing. 4, 5, 6, 7. Okay? So that 7th carbon on a triple bond is this carbon right here. Okay? And once again, we can ignore the hydrogens. And so this would represent the skeletal structure. Of this molecule. And this would represent the condensed structure of this expanded structure. Okay. All right. And so let's go ahead and get some more practice doing condensed and skeletal. And so let's just focus on this one right now. So I have CH2. And then I'm going to bring that double bond down. And then I have a CH. And so here I have a CH2. Here I have a CH2. I'm sorry, take that back. We have a CH3. Okay. And so to draw this in terms of skeletal structure, here I have carbon 1, carbon 2, carbon 3, carbon 4. So I have a 4 carbon chain. So then I'm going to put 1, 2, 3, 4. And between carbon 1 and carbon 2 is my double bond. And so if this is carbon 1, if this is carbon 2, then my double bond goes here or here. Does not matter. Okay? And that would be the skeletal structure for this expanded and condensed structure. And so for this example, we're going to go ahead and bring this down. CH3, CH, and then the double bond needs to be represented. Then here I have another CH. Then here I have a CH3. Okay, and I'm done. Now, if I wanted to pick this as a skeletal structure, I'm just going to put a reference point. I'll just change my colors. So 1, 2, 3, 4. So these are just arbitrary carbon numbering, just as a reference point. And so since I have 4 carbons, I have 1, 2, 3, 4. And if you look, I have a double bond between carbon 2 and carbon 3. And so if this is 1, 2, 3, 4, then between carbon 2 and 3, I have a double bond, and that's how it would be drawn. Okay. So hopefully you guys understand how to go from from expanded to condensed to skeletal. And you guys should be able to go from skeletal to condensed to expanded as well. Okay. All right, so here we have just a couple more. So I think I already did this one at the very beginning. And so I'm just going to go ahead and just do one more. So if I wanted to represent the condensed structure using this expanded structure, somewhat expanded, it's already been condensed for me. I'm just going to go ahead and start grouping things. So this is CH. Carry over the triple bond. And the C, the carbon. Now here I have the carbon, and I need to put that carbon first. And then I need to show the connection, just like how it's shown here. And so I'm going to put a branch from that central carbon, put CH3, and then put CH3. And actually the rest is already given for you as a condensed structure. So just copy and paste what you guys see. So here you're just going to put CH2 and CH, CH3, and here you're going to have another CH3. Okay. So then how would you depict this in terms of a skeletal structure? Once again, we need to figure out the number of carbons in our parent chain. And so I'm just going to do this very arbitrarily. 1, 2, 3, 4, 5, and 6. So it looks like I have 6 carbons. And then my first two has a triple bond. So I'm going to do a triple bond to represent carbon 1 and carbon 2. Now remember, this is 180 degrees. So we need to extend this one more in the same direction, so we're not going to bend it. So this needs to be 180. And so this is going to be carbon 3. And then now, since I'm in carbon 3, it's tetrahedral, so now I can go ahead and bend it. And so I have a methyl group at the top and at the bottom on carbon 3. Carbon 4 is another CH2. And then carbon 5 is going to be a CH, but there's going to be a methyl group attached, and it's connected to another methyl group. Okay. And so here I have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. So I have 6 carbons with trimethyl, 2 on carbon 3 and 1 on carbon 5. All right. And so hopefully this demonstrates how to draw these structures in different ways that we've discussed in the first lecture video. So let's go ahead and learn how to name alkenes. All right. So when we're naming alkenes, some parts of naming is very familiar to us. Some parts are going to be different. And so the first step in naming alkenes is to find the longest chain containing the double bond. And so since we have a double bond in the structure, we have to use ene for the suffix. And so after we find the longest chain, There's another difference between alkanes and alkenes. So remember in alkanes, we're using the ane as a suffix because all of it is a single bond. But if you even have just one double bond, that's automatically classified as an alkene. And so next you're going to number the carbon chain such that the double bond is given the lowest carbon number. And so in this specific scenario, you're going to see that there's a priority that's given to certain functional groups. And this is the first functional group that takes precedence over alkyl groups and halogens. Okay? And so halogens and alkyl groups, they're equal in weight, so to speak. One doesn't really take over the other. We just have to organize them alphabetical order. However, when we're numbering our carbons, the double bond takes priority and must have the lowest carbon number. And so we're going to identify the substituents and then we're going to name them. That's very similar to what we've done. And after that, we're going to combine everything to name the entire molecule. So let's start. Okay, cool. So this is our first example. The first thing for us to do is to find the longest chain. And I'll do that in pink, as I've always done in prior videos. And so I have 1, 2, 3. Oh, look, there's a branch point, 4. So if I go back one step, I still get 4. And so I'm going to go ahead and just stick with this. And so that means anything that it's not highlighted, any carbons that's not highlighted in pink, it's going to be a substituent. Oops. Okay. Now, the next step is to number my parent chain such that the numbering of the carbon chain gives the double bond the lowest carbon number. And so once again, I'm going to go ahead and repeat what I've done in prior videos. I'm going to go left to right, right to left. So left to right. It's 1, 2, 3, 4. Okay. And so I'm not going to add anything up. Remember, my double bond must have the lowest carbon number. And so this is where things not so much gets tricky, but I just need to clarify for perspective. So if you're going from left to right, if this is carbon 1, notice I hit the double bond while I'm currently on carbon 1. And so I'm going to put a 1 over here, right, to let me know that I'm hitting my double bond on the first carbon. Now if I go from right to left, so this is 1, 2, 3, 4, notice that if I'm going from right to left, on the third carbon, I'm hitting the double bond. So I'm going to say 3. And so once again, it looks like the winner, the lowest value is 1. And so therefore, I'm going to go ahead and cross that out. This is the wrong numbering system. And this is the correct numbering system. Okay, so hopefully that makes sense. So let's go ahead and now that we have the numbers for the parent chain figured out, we're going to go ahead and describe the substituent. So it looks like on the third carbon, there is a methyl group. And on the first carbon, the double bond starts. All right, so let's go ahead and put the pieces together. So I have 3-methyl. Now notice that since carbon 1 demonstrates that a double bond is on it, we have to tell the reader what carbon position on the parent chain that double bond starts. And it's starting at 1. So we're going to put 1, and I'm using dash because I'm going from letter to number, right? And then now I can go ahead and describe my parent chain. And since it's a 4-carbon parent chain, I'm going to use bute as my prefix. And then since I have a double bond, I'm not going to say ane, I'm going to say ene. Okay. And so what this means is that on the first carbon of this 4-carbon compound, there is a double bond. Okay. So hopefully that kind of makes sense. And the reason why I'm putting dashes is because just like the grammar that we've discussed, here we have letter to number, number to letter. So any combinations of those whenever you're going from letter to number and vice versa, you need a dash to separate the two. Okay. So that wasn't anything new. So hopefully that kind of makes sense. We're going to do several more examples just to demonstrate how we are altering some things here and there for naming these alkenes and alkynes. Basically what's the same, what's similar. Okay, let's go ahead and go to another example. All right, so first thing that I need to do is figure out my parent chain. So here I have 1, 2. Oh, look, branch point. 3. Nope. Still have lots of carbons to go to. 3. Ooh, look, another branch point. 4. Nope. I still have other carbons to go through. 5, 6. I'm sorry. 1, 2, 3, 4, 5. And so it looks like I have a 5, my longest chain that contains the double bond. So your parent must have the double bond or triple bond. And we'll see that next lecture video. And so it looks like my parent is going to be pent. So that's 5 carbons. And then since I have a double bond, I'm going to end with ene, not ane. So we'll go ahead and take it one step further. I guess I'll take it one step further later. And so now that we've figured out my parent name, which is pentene, we're going to go ahead and determine how to number our carbons. And so if I go left to right, 1, 2, 3, 4, 5. Notice that if I go left to right, carbon 3 is the first carbon in which the double bond starts. So I'm giving priority to the double bond, not the substituents. Okay? And so I'm going to say that from left to right, my double bond starts at 3, at carbon 3. Okay. Now, I'm going to do this again. Let me just erase some stuff here. Just put this off to the side. Now, if I go from right to left, this is 1, 2, 3, 4, 5. And so if I add in the arrows, if I go from right to left, notice at carbon 2, if I use this numbering system, I'm going to, carbon 2 will contain the double bond. So the double bond starts at carbon 2. So you don't really need to describe the carbon number that the double bond is ending. We always know that a double bond or a triple bond is only between 2 carbons. And so you only want to describe the carbon number on the parent chain in which that double bond and triple bond will begin, not end. And so now that I've concluded that 2 is the least, the left to right numbering system is not correct in this scenario. And so if I'm going to number my carbons from right to left such that the double bond gets the lowest carbon number, then that means that on carbon 3, I have a methyl group. Once again, let me highlight my substituents. This is a substituent, that's a substituent because it was not in pink. And so this is going to be 3-methyl. This is going to be 4-methyl. And so now that I know that my double bond starts at carbon 2, I'm actually just going to change my parent name just a little bit, and I'm going to give it a stronger description. I'm going to say that on carbon 2, I am going to have my double bond. So it kind of jumps over the number, the carbon number, and then you're going to describe it as ENE. So ENE is a double bond. And so the double bond is on carbon 2. So let's go ahead and put the pieces together. And so let's think about which one we're going to name first. So here is M and M. And so the letters are the same, so we look at the numbers, 3 and 4. So it looks like I'll go ahead and name this first. Remember, your substituents are always going to be named first. And this is going to be second, and this whole thing is going to be third. Okay. And so when we're naming this, this is going to be 3-methyl. And then 4-methyl. And then 2-pentene. Okay. And so there's a problem here. I have repeating methyl groups. And so to ensure that I'm not repeating the same item twice, I'm going to go ahead and shorten this up by putting 3, 4, so I have two numbers. Since I have two numbers, I need to put a dimethyl. Okay. And so now I'm going to go ahead and scoot this over. And if you look, I'm going from a letter to a number, so I need a dash. And so here in this case, I have 3, 4 dash dimethyl dash 2 dash pentene. Once again, this 2 is representing where that double bond is found. It's found on the second carbon of our structure. Okay. So let's go ahead and look through another example. Here we're going to incorporate some halogens. So let's go ahead and start. So the first thing that I want to identify is my parent. My longest carbon chain. What is my parent chain? And so it's going to be, I'm going to start from left to right. So 1, 2, look, a branch point, 3. Still a whole bunch of other carbons, so that's not it. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And this is, visually speaking, you can kind of already see it, hopefully, that everything that you guys see here in pink is the longest consecutive carbon chain. And so since I have 9, that's going to 9 consecutive carbons. That's going to invite me to use the prefix non. And the moment I see the presence of one double bond, of at least one double bond, I can no longer use the ane ending. I have to use the ene ending. So this is going to be non-ene. Okay. All right. And so I have to ask myself, where is this, what carbon number is this double bond found? Okay. And so I need to figure out my numbering system. So once again, if I go from left to right, 1, 2, 3, 4, 5, 6, 7, 8, 9. And so if I'm going from left to right, I see that I'm going to hit 8. And 8 is where I'm going to start seeing my double bond. Okay. So I'm not adding up any numbers. I'm just giving double bonds the priority. Okay. And if I go from left to right, the carbon that I first see the double bond is on carbon 8. Now, if I go in reverse from right to left, I have 1, 2, I'm going to erase some stuff here. 1, 2, 3, 4, 5, 6, 7, 8, 9. And so if I'm going from right to left, notice that on carbon 1, my double bond starts. And so I'm going to put 1. Okay. So this is referring to where the double bond starts. And 1 is the least, so therefore the numbering system in blue is incorrect. So I'm just going to go ahead and erase everything that is blue. Okay. So this is telling me that this is carbon 1, and the carbon number that this double bond is found is on carbon 1. Okay, so hopefully that makes sense. Let's go ahead and go through the rest of this molecule. So there's a lot of things that's not highlighted in pink. Fluorine is one of them, bromine is one of them. These two methyl groups are one of them. So let's go ahead and start describing their position now that we have now that we have the numbering system down for carbon in our parent chain. So it looks like on the fourth carbon we have a fluoro. Looks like on the sixth carbon on the parent chain we have a bromo. Looks like on the seventh carbon of the parent chain, I need to erase this. That's going to give me 7-methyl. It looks like on the 8th carbon, I also have a methyl. Okay. And so I need to figure out which of these items, which of these substituents am I going to name first. And so I need to look at the letter, the first letter of each substituent, and I need to organize it in alphabetical order. And so the B in bromo is the closest to the beginning of the alphabet, and so the B in bromo is going to go first. And so this is the English alphabet. And so here we have, so this is going to go first. And then the next one is going to be fluoro, so A, B, C, D, E, F, G, H, I, J, K, L, M. And so here I actually have 2 methyls. And so you want to make sure you combine them together and put the 7 in front of the 8. So this is going to be the third item, and I'll put this as a third item as well because I'm going to combine them together. And then the last thing I'm going to write is the parent chain. So this is going to be the fourth item. I'm going to add my final answer. All right, so let's go ahead and start writing our answers down. And so we have 6-bromo as the first item in our answer. Then we have 4-fluoro. Next we have the methyl groups. And I labeled both of them as 3 because I'm going to combine them. And so the 7 goes first, then the 8, dash dimethyl. And then the last item, number 4, is going to be that one nonene. Okay, so I've put all of the pieces in order, substituents first, and then parent name last. And so I need to make sure my OChem grammar is correct for nomenclature. So I'm going from letter to number, means I need a dash. Letter to number, I need a dash. Here I have letter to number, that means I need a dash. All right, so this is my final answer, 6-bromo, -4, -fluoro, -7, 8, dimethyl, -1 nonene. Okay, it's pretty long. Okay. However, if you go from left to right and right to left, you should be able to build this. I'm sorry, if you go from, if you take this name, 6-bromo, 4-fluoro, etc., 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 you should be able to draw the structure to get something similar to its original. Okay. Oh, what happened? All right, so let's go ahead and take a look at this example. This is just a little bit different, slightly a little bit different. We're just kind of like layering on our knowledge. And so the very first thing that we need to identify is, once again, our longest carbon chain. That much has not changed. And so I'm going to start from left to right. So 1, 2, 3, 4, 5, 6. So I see a branch point, 5, 6. Okay. And so in here, in this case, notice that both scenarios is going to give me, so 1, 2, 3, 4. It's going to be 5, 6, and 5, 6. And so which way do you go? Well, remember that your double bonds have to be in the parent chain. And so this is the correct path, so to speak, that you have to take. This is the correct consecutive number of carbons. So the double bonds, not all. So the double bonds must be in the parent chain. So you guys don't know how to name double bonds and triple bonds as a substituent. That is something that we're not going to get into. That's for the full year of organic chemistry. So for now, we want to simplify our life, and we want our double bonds and triple bonds to be in the parent chain. All right, so since we have 1, 2, 3, 4, 5, 6, the name of the parent chain is going to be, so 6 carbons, that's hex. And then notice I have 2 double bonds. I have 1, I have 2. And so since I have 2 double bonds, I just can't say hexene, very similar to if I have like 2 methyl or 2 ethyls. I have to say hex diene. So the di means I have 2 double bonds. Okay. And so let me see here. It's actually, I take that back. It's not hex, it's going to be hexa. I need a vowel. So hexadiene. Okay. And so since I have 2 double bonds, I have to tell the reader where those double bonds are found on the parent chain. Okay, so that means I need 2 numbers to go in front of my hexadiene. Okay. Right, so I have 2 double bonds, as seen in the blue arrows. So let's go ahead and continue. That means anything that I didn't highlight is going to be our substituent. Now, before we figure out how to name our substituents, we need to number our carbons correctly. And we want to make sure that the double bond has the least carbon number. So I'm going to start skipping some steps here. I need you guys to kind of see this visually. And so if you look, if I go from left to right, I already have carbon 1. Okay, so carbon 1 is where my double bond starts. So that lets me know I don't need to go the other way. This is the only way that's possible. And I apologize, I also have another substituent there. And so therefore, my numbering system is going to be 1, 2, 3, 4, 5, and 6. So on the first carbon, that's where one of my double bonds will start. And on the fourth carbon, that's also where the second double bond starts. And so I'm going to go ahead and put in here 1, 4 dash hexadiene. That's telling me that I have a double bond on the first carbon and I have a double bond on the fourth carbon. Okay. So now that I've figured out the double bonds, now that I've figured out what carbon number my double bonds start, I'm going to go ahead and start describing my substituents. And so here I have an ethyl, and ethyl is on the fourth carbon. So I'll say 4-ethyl. Here I have a chlorine on the fifth carbon, so I'm going to say 5-chloro. Here I have a methyl group on the second carbon, so I'm going to put in 2-methyl. Okay. And so now that I have all of my substituents named and labeled, I'm going to go ahead and put them in alphabetical order. And so it looks like the first letter that I'm going to start off with is going to be chloro because it starts with a C. So this is going to be named first, A, B, C, D, E. So this is second. And then M is third. And finally, I'm going to name my parent. So that's the fourth item I'm going to use in my naming of this compound. So let's go ahead and combine all of this together based on what I just identified. So I'm going to write 5-chloro first. And then I'm going to write my ethyl second. I'll do that later. So 4-ethyl. And then my 2-methyl is going to go next. And then finally, my parent chain, my 1,4-hexadiene. So 1, 4 dash hexadiene. Okay. So I've placed all of my pieces together in the correct manner. So the next thing I'm going to do is just make sure that my connections between these pieces is correct. And so letter to number, dash. Letter to number, dash. Letter to number, dash. And that's my final answer. Okay. 5-chloro, 4-ethyl, 2-methyl, 1,4-hexadiene. And so whenever you guys are working with a substance that has organic compound that has 2 double bonds, you have to use the prefix di, tri, tetra, etc., etc. And then you guys have to describe where each of those double bonds are located on the parent chain. So you have to give the same number as there is if it's like di, tri. So if it's di, you need to provide 2 numbers, such as like 1, 4, right? Just like this example. If it's triene, that means there's 3 triple bonds, and you need to tell the reader what carbon number it's found, so to speak, if you go from like left to right or right to left. And so hopefully this helps introduce that concept to you, and we'll go ahead and do one more. Okay. So this is going to be the last example for this video. All right, so same situation. We need to figure out carbons and carbon numbers. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So let's see if we can backtrack a little bit. So we have 1, 2, 3, 4, 5, 6. So 6 is less than 9. That can't be it. 1, 2, 3, 4, 5, 6, 7, 8. So 8 is less than 9. And so visually speaking, this is probably like the longest consecutive carbon chain that contains all of the double bonds that's present in this molecule. And so we have another 9 carbon compound. And so the parent chain is going to be a 9 carbon compound, and that's going to be non, okay, that's 9 carbons. And here I have 1, 2 double bonds, and so I need to put in nonadiene. And so I just need that vowel to separate the two consonants, the N and the D. Okay, so just think about like nonane, and then you're just going to cross off the NE and add diene. Okay. And so since you have di in front of this ENE, so that means I have 2 double bonds. So I need to ask myself where those 2 double bonds are in the carbon chain. And so we need to figure out our numbers. Okay. And once again, since we're dealing with double bonds, the double bond gets the lowest value, the lowest number in the numbering of my parent chain. And so it gets priority over the halogens and the alkyl groups. And so since I see that my double bond already starts at carbon 1, I'm just going to go ahead and put in 1. Okay. And so there's no point for me to go backwards and say that this is 1, because I've already figured out that carbon 1 contains my double bond, and the double bond gets priority. So this is 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, and so now that we have all of the carbon numbers down, let's go ahead and start identifying where the double bonds are in the parent chain. So I have a double bond starting at carbon number 1. And so I'm going to go ahead and put in a 1 here. Since I have 2 diene, I need a comma. And if you look at carbon number 2, that's where the double bond ends, so I don't need to include that. If you look at carbon number 3, that's where the second double bond starts. And so I need to put a 3 here. And if you look carbon 4 is where the double bond ends, but we don't care where it ends. We're not, we always know that it's between 2 carbons. So if you say carbon 3, it's implied that the double bond is between 3 and 4. And so therefore you can just go ahead and put the dash, because you're going from a number to a letter. And that will fully describe where those double bonds are located in the parent structure. All right, so now that we're done with the double bonds, let's go ahead and do the substituents. So anything that is not highlighted in pink, that's going to be my substituent. And so this is telling me that I have a methyl on carbon 2, so 2-methyl. This is telling me that I have an ethyl, so I have 1, 2, carbons on carbon 4, so 4-ethyl. Here, this is telling me that I have a methyl on carbon 5, so 5-methyl. This is telling me that I have 2 carbons, so that's another ethyl on the 6th carbon. And this is telling me that I have an iodo on the 7th carbon. Okay. So now that I have labeled all the pieces, all the substituents, I need to figure out which of these substituents I'm going to name first. And so I have to do this alphabetically or in alphabetical order. I have E, okay? So probably this one is going to go first because it's 4, and then this one's going to go like second, if you will, or I'm going to combine them. So this is 1A, 2A, or I'm sorry, 1A, 1B. Okay. And so I have the E's, and then the next one is the I. So this is probably the second piece of I'm gonna name, and then I have the methyl. So this is probably 3A, and then this is 3B. The reason why I'm putting A's and B's is because I'm going to combine them, right? They're both methyls, they're both ethyls. Okay. And so the last item I'm going to add in my naming of this compound is my parent chain. Okay. So now that I have all the pieces, I'm going to go ahead and start putting them in order as I numbered it. So I have 4-ethyl that's going first. And I'm going to combine that with the 6-ethyl. And so I need to change, and I need to put this together. So I'm going to put in 4,6-diethyl. Okay, so that finishes this and this. Next is iodo. So 7-iodo. And the next one is 3A, 3B, so that means I'm going to combine them. So 2-methyl, 5-methyl. So this is going to be 2,5-dimethyl. And then the last item is going to be 1,3-nonadiene. All right, so the last thing that I need to do is just connect all of this. So here I have letter to a number, dash, letter to another number, dash, letter to another number, dash. So it turns out that there is all dashes between each piece, and that is the name of my organic compound. And so when you guys are doing this, just take it step by step. Try to see and understand the pattern of how I'm solving these problems. Yes, I am kind of changing how I'm presenting it per scenario, just ever so slightly. So for example, sometimes I don't put in the 1s and 2s and stuff for some of these previous examples, but I'm just basically providing you guys all the tools to help you guys organize your train of thought, to help you lessen any mistakes in terms of naming these organic compounds. Okay. And so now that you have the name of all of these compounds, try to go backwards. Try to, draw the skeletal structure 4,5-chloro, 4-ethyl, 2-methyl, 1,4-hexadiene. Okay, and see if you got something similar to the original structure. So that's pretty much it for this lecture video. I'm going to go ahead and talk about how to name alkynes in the next video. All right, see you later.